Have you ever wanted to be the first to know if aliens really exist? Well, with Nebula, you can be! Nebula is the streaming service that's home to It's Probably Not Aliens, as well as our YouTube channels. And the best part? All of our content goes up early on Nebula. So when we break first contact with ET, you'll be the first to find out. That's right, you'll be able to listen to the next episode of this show before anyone else. Plus, we post bonus content that you won't find any other place. And the best part? By signing up for Nebula at nebula.tv/probablynotaliens, you're directly supporting the show and both of us. So don't wait any longer. Join Nebula today and be the first to know if this time it really is aliens. So, the first thing we need to talk about, what are some things, I want your most controversial things that you think are overhyped.
The most controversial things I think are overhyped.
Like you finding it overhyped is going to be a controversial take.
Okay. Like me, Scott specifically, or just in general? Okay. Oh, me, Scott specifically. I think hair is overrated. Hair on the top of your head is overrated, Tristan. That's what I think. I think it's overrated.
Oh boy.
No, I would say, gosh, I don't have a good example here. I wish I thought of one. The ocean is overrated.
Don't
need it. Who needs it? No one's living there.
Aquaman begs to differ.
That's fair. I do love Aquaman.
Or whatever. What's his name?
Namor's also down there.
Namor.
Why not?
They're married.
MCU, overrated. We got Superman now, all right? We don't need the MCU anymore.
Yeah, that's a decent one. I mean, but I feel like also that's getting popular.
That's the cultural consensus, I feel. Yeah.
COVID killed the Marvel Cinematic Universe. Let's just put it there.
That's true. That's all I got. Can you give me some better ones?
Okay, the one that comes to mind recently, and this is one that I think is less controversial than it was a few years ago, but Gloomhaven. So, sorry?
I was just repeating. Gloomhaven sounds cool.
It was an absurdly popular board game a number of years ago.
Mm-hmm.
And it came to define the board game industry for the decade following it. But it is a extremely expensive, extremely large box with lots and lots of pieces, so much so that you typically have to buy a tackle box to go alongside the box so you can put all the pieces in it.
Yeah.
And it is very bookkeepy, onerous, and it wants to be a video game made of cardboard and makes the game is a giant pain in the ass to set up and play.
All right, this is the thing. I've never played Gloomhaven, but I do know friends who are board game people. And they have all the board games, just displayed, all the popular ones displayed out. And that's one of them that it's displayed out. When I say displayed, I just mean the box is prominent. It's not hidden away in a closet or anywhere. As a part of their home, Gloomhaven is there. And anytime we visit those friends and they're like, we should play a board game, my mind and my eyes always shift over to the big Gloomhaven box. And the people who own it go, not that one though.
Yeah, well, the thing is that it has the game can have, it's a campaign game, which means you have to play multiple things in a row. It has 90 plus scenarios. And you have to put all the pieces together, but then the missions usually boil down to go to a room or kill everybody. And it's just kind of there's a whole bunch of random bookkeeping stuff and cool ideas if they were in a video game, but then they're actually, but you have to do it where you have to manually manage everything yourself.
That's
but that's one I
have another underrated or an overrated. Are we just doing overrated, not underrated?
Overrated, yeah.
Fully overrated. This is just gonna be I'm becoming old sort of a thing, but not really. I have a lot of smart home technology in my home, mostly lights, which helps with the office, like lights and shutters and things like that. And it's great for what I need it for, but it is, once I lose the appeal of like, isn't it fun to like set up these fun like automations? Like we just got a smart thermostat and it is fine, but it's like it has caused smart lights and smart thermostats and smart home stuff has caused more confusion with just like having guests or even just having my wife who just wants to use a physical switch on the wall and not have to go to her phone and turn the light down. And I get that. I think it's overrated currently. I think it's fine for what I need it for in my office space, but putting it throughout the home has been a mistake.
I can get that. Yeah, I got a Nest that came with the house. And
there you go.
It works fine until like Kelly broke her phone and then had to get a new phone. And then I went to work and the Nest didn't know that she was at home, and it has a thing set up where so it's like, I will turn the air conditioning off because there's nobody in the house right now, so we'll conserve power. And Kelly was like, it's burning. Mm-hmm. So she had to reconvince the house that she was in it so that it would use air conditioning.
It's been a pain for sure.
Another overrated thing, I had it and then I lost it, but
okay. I can give you more underrated stuff, which is basically like stuff that I like that I don't have an outlet to talk about. But I don't have a lot of overrated stuff because if it's overrated, I tend to just forget about it. And I don't think about it anymore.
Something that's really popular that you don't think is, you know what? Like every Instagram restaurant, the first time I ever went to a place like one of those like stupid big milkshake things, and I was like, this thing sucks. And the only reason it was popular is because they made an aesthetic thing for Instagram. Instagram in general. Maybe that's my old man thing. It's I don't get it. I don't.
Yeah.
I don't get Instagram. I've never been able to like go on Instagram and be like, wow, this is fun. Obviously people like, I get like a dopamine hit from it for some reason, but I'm just like, nah, Instagram never does it for me.
And while we're being old men, I also have I'm gonna say what else is overrated? My marriage. I'm a big old boomer.
I do not endorse this.
I love my wife very much. This has all been a joke, except I also don't get Instagram.
You know what else is a joke?
Yeah, what else is a joke? Tell me.
This podcast. It's a podcast called It's Probably Not Aliens.
Podcasts are overrated.
They definitely are. Let's not mince words there. So this is a podcast where we do stuff about ancient aliens, ancient astronauts, UFOs, conspiracy theories of a science fiction and extraterrestrial variety.
Yes.
You're Scott.
I'm Scott Nicewander. I know nothing. I don't even know what was overrated. It took me so long to figure out things that were overrated. I don't even know why we did that. Was that going to be a part of the episode, or is that just a fun thing you wanted to pick my brain about?
It's related. Comment below this podcast or however it is that you do that.
Yeah.
You said you were looking for like engaging material. Tell us what's overrated.
Yeah.
Give us the really spicy, deranged ones, you know?
And who else are they addressing those comments to other than me?
I'm Tristan Johnson. I'm the one who somehow keeps finding ways to convert lunch breaks into content, like today. So I want to talk about...
Yes, I understand this is sort of an emergency, not really kind of an emergency. It's sort of a break from our theme this season, but...
Yeah.
Yeah.
This was on brand. It's on brand, but it definitely isn't like about angels. And it's not like it's not even really about debunking pseudoscience, which I think is an interesting angle. In fact, this is kind of about how we can sometimes get carried away when talking about real science and overhype results.
Okay, I get it now.
And that is, and it would have been an emergency episode if we had released this like 3 months ago, but. Did you know, Scott, that we learned that several hundred light years from here, we found a planet made of farts?
I have a new sound on the soundboard for this exact occasion.
I'm sorry. I was going to try to keep a straight face. I just can't.
It's always funnier than I think it is.
Yeah.
I want you listeners to know I just had this already produced on my computer. And when Tristan shared with me the outline for this episode, the very first word I saw was farts. And I was like, I can load up my dramatic fart.mp3 file onto the soundboard if you need me to. So I hope it was worth it.
Yeah, we are all still children.
Yep.
I'm sorry. Okay, so I want to take you back to ancient days, to April of 2025.
Oh, man. What was even going on then? I was trying my best to get a video out in time for 420 about if Shaggy from Scooby-Doo is a stoner. I didn't do that one. I failed that pretty miserably. I don't know. Was there any fun April Fool's Day jokes on the internet? I think they stopped doing that. So I don't really know what was going on back then.
Nobody does. It's lost to history. Mm-hmm. But one thing that did happen in April of 2025 is Cambridge University, the British place.
The British place, yeah.
They dropped a big one.
They sure did.
Yeah. So what happened was
dumped a huge load of science on us or something, I'm sure.
Yeah. They blasted us all with their science. We learned about something that happened on a planet several hundred light years from here. And what we found is that there might be a material called dimethyl sulphide on an exoplanet called K2-18b.
All right.
Named after its discoverer, Roland K2-18b. One of Elon Musk's children.
Yeah. The contemporary philosopher, yeah.
Yeah. So this was made by, this discovery was made from the James Webb Space Telescope, which produced a lot of excitement because dimethyl sulphide, which does have sulfur in it, so it would smell like farts.
Okay.
Is actually on Earth only produced by one thing, and that is marine phytoplankton that fart out these sulfur compounds. Phytoplankton notably being living things.
Living thing that makes this chemical. That's kind of, it's not even kind of cool. That is cool.
That is the detection of a chemical that only living things produce on a planet 200 light years or several hundred light years away. So that is potentially, and I remember the news was very keen on saying this, proof of alien life.
Incredible. Is this the closest we've ever come to like evidence, official evidence? That's probably hard to judge.
I mean, the thing is that it's with this James Webb Space Telescope, like we might find more things like this, which is interesting.
Okay.
But everyone's like, oh my goodness, so this is like the first confirmed biosignature of another planet, 124 light years away.
Just around the corner.
Yeah. So, the media went crazy, life evidence for alien life. If you look at it, the results show that there was probably 20 times the amount of dimethyl sulfide on this planet compared to Earth, which means that there was a thriving
stinky planet.
It's a stinky, a thriving fiber-rich ecosystem. It's the planet. What are those? Oh no, there's a good joke there.
They're eating their Wheaties.
That company that makes beans. What's the bean company?
Oh, Bush's Baked Beans. That's what we have here.
K2-18b. The B stands for Bush's Baked Beans. Okay, so why are now? But the thing is, since that discovery came out, people are starting to say, well, maybe not. Maybe this actually wasn't the case. Maybe this isn't alien life. But the thing is that the controversy surrounding it actually reveals a lot about how we do search for aliens and how as James Webb looks at more exoplanets and makes more of these discoveries, how we're going to actually narrow down and determine whether or not something is life. Okay. And I think that we learned a lot from there. And I feel like that fits under the umbrella of this podcast.
I think it's close enough, and I'm excited to learn about alien farts or just Non-alien related farts.
Non-alien farts, NAPs, or NAFs.
NAFs. Yeah, I think we both thought it was a P for some reason.
Yeah. But how did this story about the potential that we were going to alien life turn into a whole thing that talks about how we do science, how we communicate science, how the incentives for scientists and the incentives for universities led to us thinking that there was a fart planet that we were going to that was going to be full life, and so that is what we're going to talk about today.
If Star Wars has taught me anything, is that there is a planet for every conceivable type of atmosphere or condition, right? There's going to be your desert planet, a whole planet of desert. There's going to be your water planet, a whole planet of water. And there's going to be a fart planet, a whole planet of farts. And they cowards over at Disney have yet to bring that to The Mandalorian. As far as I know, I did not watch the last season of it, though. So if they did that, you'll have to let me know, and I will apologize.
You know what? They're probably running out of ideas on freaking the Star Wars people.
They ran out of ideas the second they kept bringing Luke back for everything. What's the one idea we have for Star Wars? Oh, the Skywalkers? Oh, this the smallest galaxy in the world because they're connected to everything. It's just the Skywalkers? Yeah. We can't think of anything else? Anyway, don't get me started, Tristan.
So in a long time ago, specifically 124 years ago, in a galaxy that is the one we live in, and not actually that far away in the great scope of things, there is a little planet called K2-18b, and it is what we like to call a super Earth.
Okay, big Earth.
Yeah. James Gunn also directed this planet. So a super Earth.
Canonically, DC Comics, the Earth on DC Comics is bigger, slightly bigger than our own Earth. That is canonical.
Oh yeah, because they have to fit all the fictional cities into it, right?
Mm-hmm. Yeah, something like that.
Okay, so K2-18b is a super Earth because basically James Webb is still not, like, we do not have the technology to be able to detect a planet that is like the size of Earth that far away. If you think about it, think about how hard it would be to just to what they're doing here. So I don't know if you know much about how we find exoplanets.
We look for them.
We definitely do that.
Awesome.
Okay.
I assume we don't just use our eyes in a big telescope and just scan from left to right all day.
No.
Yeah.
Okay. So the thing is that we wouldn't actually be able to see a planet that is that far away. They don't emit light, right? They are and they are hundreds, if not thousands or bajillions of light years away, farther away than like we could ever deal with. So instead, we have to figure out novel ways of finding these planets. And the ways that the astronomers have figured out is that you look at the star, because the stars do emit light.
Mm-hmm.
And if a planet's orbiting it, like, planets do have a gravitational field of their own. We pull on the sun as much as, well, not as much, but we do pull on the sun as the sun pulls on us.
Okay, yeah.
Right? So what they've been able to do is, if you watch one star for a very, very long time, you'll start to find a little bit of a wobble. And doing some mathematics on that wobble, you can then figure out that there's a planet around it. And they've learned now enough that they can figure out stuff like how big it is, how far it orbits from the planet, those kinds of things, and how many there are. Like, for example, the TRAPPIST system is another star that we found that has like 7, I think, planets that are in its habitable zone, which is like where the habitable zone is the distance from the sun where it could have liquid water on its surface.
Gotcha. That sort of Goldilocks zone.
Yeah. So K2-18b has is about 2.5 times the size of Earth, about 2.6 times exactly, but is 8.9 times heavier. So it's very dense, it's very heavy and very big.
Yeah.
Because if you think about it, because that's the way that we're discovering planets, you can imagine that the ones that we are finding first are the ones that are very dense and very big.
Yeah, the literal, like the massive ones in a literal sense. Yeah.
Because another thing that we do to measure size and stuff like that is that if we watch that star long enough, we'll watch the planet kind of get between us and the star, and we can tell by how much the star's light dims that we can like infer some information about its size and stuff like that.
And that's going to be much easier to detect if it blocks more light.
Yeah, exactly. So the thing that we used is the James Webb Telescope's MIRI, which is called a mid-infrared instrument, and then doing something called transit spectroscopy, which I'll talk about later.
Okay.
But it is a technique that is being used to not only find out that there are planets, but what is in its atmosphere.
Well,
and that is where...
No, go for it.
And that is where we found that when a planet that orbited this star, which is a red dwarf called K2-18, not surprisingly.
Love it.
We found the signatures of either dimethyl sulphide or possibly dimethyl disulphide.
Now, can I just say, for a technology that can do all of that, it's literally like finding planets and finding, what it can be made of and things like that. I think it's a little hard on itself to call it the mid-infrared instrument. I think it's more than mid. I think it's pretty cool, actually, and pretty good.
Pretty based.
It's pretty based. I would say it's the based infrared instrument.
Yeah, it ate left no crumbs. James Webb Telescope.
It found that planet the long way. You know what I mean?
Mm-hmm. Yeah. So the other thing, too, is that as the study happened, they discovered that there were 10 parts per million of dimethyl sulfide on this planet, which is compared to Earth, where we measure it in like parts per trillion. So even possibly thousands of times higher concentration of dimethyl sulfide on this planet than on Earth. And also, to bring back more fucking brain rot words, they also found that the likelihood that it was random noise was around 0.3%, which in science terms is called 3 sigma.
Something that wouldn't exist on Earth, okay? Because if you're a true sigma, you wouldn't be with 2 other sigmas, all right? There'd never be a concentration of 3 sigma. Wouldn't exist, all right? That's beta activity.
Yeah, exactly. So that is a term that means that it describes how the data is distributed and, a sort of bell curve thing. And it defines that, like, basically there's a range that extends 3 standard deviations above and below the mean, which means that there's about a 99.7% chance that these data points are something that is not what they're seeing. It's like how confident you are. They are 99.7% confident that this is what they found.
That's really confident.
It's very, very confident. We'll find out that confidence is, standards are different.
Okay.
Yeah. So we started seeing apparently this team started seeing hints of it in 2023. But as you can imagine with that sort of the way that we look at exoplanets, that you need to watch multiple passes in order to get more confident in the data that you're collecting and what is happening. So in 2025, they decided to make stronger claims and published it. They published it, and the lead researcher who did this is a professor by the name of I should have practiced this one.
You got it.
Niku Medhusudin, who's focused on exoplanetary research and has a whole team of students and scientists who are working on studying new exoplanets.
Yeah.
Specifically, these characterizing of exoplanet atmospheres using atmospheric retrieval techniques, which I'll talk about later. And they have won several, this is not something that is wacky. This is not pseudoscience. This isn't fringe. This is a team that has been published widely, and they have gotten several international awards for their contribution to exoplanet science, including the coveted Mirac Prize in Theoretical Astrophysics and the IUPAP Young Scientist Medal. So, these aren't cranks. These are, very much people who are leading in a very, very cutting-edge field.
All right. That's why the confidence is all the way up to 99.7.
Exactly. So the next thing I want to talk about is what is dimethyl sulfide, and I'll get it. And
Gosh,
so
I
what
thought
that
you'd
is,
never ask. Oh
yeah.
goodness.
Now, as every child knows, dimethyl sulfide, which is defined as CH32S, is two methyl groups, i.e., two CH3s, attached to bonded to sulfur. Sulfur being a material that is found abundantly on Earth, and we probably all
And
know
in
it best
hell.
because and in hell, because its old name was brimstone, and everyone knows sulfur mostly because it smells like farts. We
Yeah.
add sulfur, and that is where it comes from. That's what fart smell comes from, sulfur, because it's from the sulfur in the food we eat.
Can I say, as a kid, I got this confused with sulfa, which is a drug that I am allergic to, but I didn't know that sulfa was a drug. I'd only heard of sulfur. So when people would ask me what I'm allergic to, and I would say sulfur, and they'd be like, "How? Don't ever fart."
Yeah, your body literally needs it to live.
Yeah.
So sulfur is it's yellow. You'll probably like when it's mined, it's like very smelly. We do stuff like it's got a bunch of uses for a lot of different purposes, but like one of the purposes is like we add like a compound of it to propane so that it gives us a smell. Like it does all these things.
Yeah. Which is good. We want it to smell so that we know if there's a leak.
Yeah, exactly.
Or something.
Like for example, we use sulfur to make acid. You've probably heard of sulfuric acid. It's probably one of the most common industrial acids out there. It's used in fertilizers. It's used in pesticides. It's used in the. Have you ever heard of vulcanized rubber?
Yes. Have we talked about this on the show before? I can't remember.
I'm not sure, but rubber is like, like it's basically a kind of tree sap, and it used to have a lot of trouble keeping its shape. Like sometimes if it was too cold, it would freeze and it would crack, or if it was too warm, it would melt. So people's like rubber boots would melt until they discovered how to vulcanize rubber, where you add sulfur to rubber and it gives it a lot more stability. And that's how we've been able to make things like tires and all of the rubber things that we use.
So good that tires don't melt on roads. Huge for us.
Yeah, and like, matches, explosives, we use it in the petroleum refining process. It's used in some like oftentimes it's used in like topical creams that we use for scabies, like the parasite that lives in your skin. But it's also used in like some dandruff shampoos have sulfur in it.
Okay.
And it's also part of our fucking like DNA.
Yeah.
So it's like
would be tricky to be allergic to it.
Yeah, but it's a critical component of life. Marine phytoplankton and some bacteria, when they decompose organic matter, create dimethyl sulfide. On Earth, DMS is almost exclusively a biological process. And we found it on this planet, K2-18b, specifically using something called spectroscopic. Sorry. Go for it. Using spectroscopic absorption lines at infrared wavelengths. So this is one of the coolest fucking things that exists, and like it was discovered like in like the 18th century. I don't want to say Newton discovered it because that feels like it's wrong somehow, but it was like from like that kind of period of scientific discovery.
That early, huh? Wow.
Yeah, and so here's what this is, and this is fucking cool. One of the examples you might find of this is the principle behind this is sort of like how things like fluorescent lights work and stuff like that. So what you'll do is if you look at electromagnetic wave, like electromagnetic light, so say light hits me, it goes through a prism, you can take white light and turn it into a rainbow, right?
Yeah.
The thing though is that if you take light, say of burning carbon or burning, I don't know, sulfur in this case, and you do the same thing, you're gonna see little lines. They're tiny and they're hard to see, but they're little lines. And what these are is that atoms or molecules absorb photons at very specific wavelengths. And when photons hit them, when they absorb photons, the electrons in their like if you remember your Bohr-Rutherford diagram, like the sort of rotating electrons have like shell levels and stuff like that. So when they absorb light at specific wavelengths, they'll excite electrons to a higher energy thing, to a higher energy state, which is called photoexcitation. This is what we do to like the gases that are inside like neon lights and stuff like that to make them go. So different gases cause different lights to happen. And that's how you get like the different lights in like, say, like a neon sign or something like that.
This reminds me of, if I can bring pop culture into it, this reminds me, are you familiar with Mary Poppins?
I think so. I remember I've seen Mary Poppins, the 1960s movie. Could not tell you a detail of what happened in the movie.
Doesn't matter.
I saw the Mary Poppins sequel that came out like in 20-something, and also do not remember a single thing from it.
That's fine. The original, all you need to remember, if you can, is how much green screen they used to like put them in a cartoon world with the penguins and other cartoon things and whatnot. Except it wasn't green screen, Tristan. This was a technology that was, I believe, I could be wrong, but I believe really just used for this one movie, and maybe that's it. It was called a sodium vapor process, and rather than a green screen, it is lights shining one extremely precise and specific wavelength of yellow light that the film that they were using was able to sort of like filter out and have like a composite, or if it was like post-processing, they were able to composite it very easily because it was like this one specific wavelength that this sodium vapor process was creating, and is also, I believe, the same or similar to like street lights. It's like a street light yellow. It creates a very specific yellow. Yellowy gold sort of a thing, and that's how they were able to achieve like really astounding compositing back in the day, like being able to see through like semi-transparent objects even without much work, because it was able, like clothing and cloth and things, they could have like semi-transparent and be able to still composite it with like no problem, because they were using this extremely specific chemical light process. And I just thought that was a really interesting way to use this sort of thing in a creative way.
Yeah, like that is whenever I watch like Technology Connections brings this up sometimes, but like we used to be really, really clever before we could we'll just computer it.
Yeah.
So we used to have to think of really interesting workarounds before then, and that's a really cool one. So to kind of like show like how we do this with like materials, if you take light that is from a material and you run it through like a thing, you'll like through like a sort of prism or something like that, you'll get a spectrum that has these little black lines. And because like when they absorb that wavelength of light, that means that those specific wavelengths of light are no longer being reflected out, right?
Mm-hmm.
So what you end up getting is like the full rainbow with like little gaps where those molecules or atoms are absorbing the light and exciting the electrons rather than like just reflecting them.
Yeah.
And so you end up with like these little things that have like, a rainbow with like a bunch of little black lines. And we've been able to figure out like, this combination of black lines means this combination of black lines means this, and et cetera, et cetera. So every element produces a unique set of absorption lines at precise wavelengths that kind of act as like a fingerprint. And all that energy state stuff is like a bunch of shit to do with quantum mechanics that I can't super explain because Angela will get mad at me. And so I have to like,
that's fair. That's fair.
But also like, how wide the absorption lines are and how deep they are can show a lot of information about its composition, its temperature, its density, and even its concentration. So what you do is if you look at the starlight when the planet is passing in front of it, because remember how they did that to the dip in its light to find out how big and stuff it was.
Sure.
You can also take the light from the star when the planet is going in front of it, and you will get the spectra of the atmosphere of that planet.
That is so cool, man. That is so cool.
It is what it is. astronomers are freaking geniuses. That is like one of the coolest concepts I ever have heard in my life.
I've always wondered this as a kid of like, how do we know what the other planets are made of? And
this is exactly how we do it.
This is, and the fact that we can do it from hundreds of light years away is incredible.
Yeah. And we have been using this for astronomical stuff, to study gas clouds, to study planets, to study stars, and figure out the composition of things that we could never actually get to. So like, I actually even included a little picture here so you can kind of see what it looks like when you look at it at a thing. But you can see like nitrogen has like a specific signature and everything, like hydrogen, et cetera, et cetera. And so you can kind of piece these together and find the answers.
Yeah, they really are. Now, you sort of said it. They really are sort of like fingerprints in a way of just being like, oh yes, I see the pattern of the sort of wavelengths that are emitted. And so I know that it's this chemical and whatnot. It's so cool.
Yeah. Now, I did say that one of the fundamental issues we run into is that with current technology levels, James Webb doesn't have the capacity of like detecting a planet that's like our size. They can really, like at the moment, we're really looking at planets that are like still a few times larger than Earth. We're trying to get it smaller, and things are getting better all the time, and it's really good that it's also tied to developments in digital camera technology, as we'll learn later. So as those get better, we'll get better, satellites that can then do stuff like this.
And can I point out as well with this chart? So we'll try to post this on Blue Sky and whatnot, but there's a chart of all the what is absorbed and what's emitted from different light is absorbed or emitted based on different chemicals: sodium, nitrogen, hydrogen, oxygen. Now I was talking about the sodium vapor lights, which I did look up and do a little bit more research on as you were talking. And they are used, or at least have been used, in street lights as well. In fact, the Wikipedia entry is a high-pressure sodium street light in Toronto. That's the image of it. But they produce light at a very specific wavelength of like 589 nanometers. And this chart you have, if you look at the sodium one, right before the 600 nanometers on the sodium chart is it is emitting a bright yellow, like almost pure
Isn't
yellow
science
light.
cool?
That's so cool. Look at how all this stuff is connected. I love it.
Yeah. So the thing that to kind of get onto the thing about like these big planets is the problem is that none of those planets would be like, it'd be too much gravity for life to really work. At least life as we know it, except that one of the proposed theoretical types of planets that could support life that we could see that would have a size that we could detect are what are called Hycean worlds.
Ooh.
And what these would be are basically ocean worlds. They would be large oceans that have hydrogen atmospheres.
Okay.
And that life could live in the water on that planet, because they wouldn't have oxygen in the atmosphere. Like there wouldn't be oxygen, there wouldn't be gaseous oxygen. The atmosphere would be all hydrogen, but there would be oxygen dissolved into the water. And in the parts of the ocean world that aren't dense enough that they would kind of be like almost like, because of gravity would become like, or pressure, water pressure would be like almost, depending on the size, could almost be a solid. But there's a band in there where you could have, the chemistry of life be very doable, even on a planet that's a lot bigger than Earth. And so that was what they were looking for, and that's what, when they came to K2-18b, suspected we might be seeing here. Now, what went wrong? Why is it that this is not...
Why is there? No. Let's end the episode. It sounds great. What do you mean? What went wrong? This all sounds great.
Why is this not, or maybe not, or potentially not, a thing?
Probably not. Let's use let's use our branding.
I can't even bring myself to say probably, as we'll learn. But why did we jump the gun? Is the answer, and we'll find out after a very quick product or service break for sulfur. Buy sulfur.
Yeah, and I'm just going to hit our regular button that I hit to play our regular music. And this is the button.
Go, ads, go.
Hey, you know that feeling of total exhaustion you get from being online? That sense of powerlessness against an endless wave of grifters and bad faith arguments? Well, that's by design. The whole environment of online spaces right now is engineered to make you feel angry and overwhelmed to increase engagement metrics. This is like not some conspiracy thing. They've literally said that anger is one of the most evocative emotions and helps with increasing engagement metrics, which means more ads, which means more revenue. But it also wears you down and reduces your ability to fight back against, well, gestures widely. And that's why we, at It's Probably Not Aliens, decided to build our own spaces. And it's one of the many, many reasons why this show is on Nebula. Nebula is a streaming service built and owned by me and a ton of other creators you already trust. Think of it as a curated library for thoughtful videos built from the ground up to be a better experience. It's a place for exclusive content without ads, designed to arm you with ideas, not exhaust you. It's also the single best way to support this show. As a thank you, all our podcast episodes go up a week early on Nebula, and we do an exclusive full-length Q&A episode there every single season. Now, for those of you who are in this for the long haul, I also want to mention the lifetime plan. The price for that just went up to $500, but our link still gets you lifetime access for $300. You pay once, and you are done. It's a huge way to support independent creators, and that's what we're building. Plus, if you're like me and tired of the subscriptions, this is a way to just pay once and never think about it again. You have Nebula forever. So whether you want to go monthly or join for life, turn that frustration into action. Start building something better with us. You can sign up at go.nebula.tv/probablynotaliens. The link is right there in the show notes. Join us. It's worth it.
And we're back. Wow.
We're back, baby.
This is what we make the big bucks for.
How many toots did you let out during that ad break? Let us know on Blue Sky.
Okay, so here's the thing. So the first thing we need to talk about is the 3 sigma thing, the 99.7% sure.
Right. Let's talk about these 3 sigmas.
Yeah, so I had to talk to my wife about this one because I am a certified not scientist. My wife
is certified in that. That's nice.
Yeah, my wife doesn't work as a scientist, but was a psychologist. She has a PhD in psychology, so she actually has done statistical, experimental research and has had to calculate things like this, like confidence numbers. And 3 sigma is an absolutely huge result if you were doing something in psychology, but social science is a much more messy field than physics. And in physics, there's a much higher standard of evidence because if you think about it, especially when you're working with things like at the quantum level, when you're working with atoms and you're working with extremely sensitive equipment, you want to be, and also in cases like this, working with things that have huge ramifications if they're true, and on top of that, are going to like if a piece of physics, like if a new law of physics is discovered, immediately we're gonna be building the mathematics on top of it and all sorts of stuff. So it needs to be really confident, or else we could just have a whole bunch of science ruin everything.
Yeah.
Or a whole bunch of science collapse when something is taken out of that process. So in physics, something isn't considered a real discovery until it gets a confidence of 5 sigma.
Whoa.
Yeah.
That's impossible. 5 sigma?
Yeah. So 5 sigma is about a 0.000006% chance of error. So that is 5 zeros and then a 6.
Good Lord. 1, 2, 3. You wrote 4 here. Is that correct? 4 or 5? I want to make sure we get the number right.
It's 4 O's and a 6, so 5 digits.
Oh,
sorry.
I see what you mean. All right. Yeah. Sorry for interrupting.
Yeah,
I just didn't want to have to do a correction episode on a small
no worries. Very small. I am Definitely not 3 sigma confident, but
I was
close
gonna
enough.
say your wife is pretty familiar with sigmas because she's living with one, buddy.
Okay, so the thing is that we have had there's a high stakes nature aspect to it. There's also the fact that there's been several times in the past in particle physics where we used lower confidence variables or lower confidence levels, and it resulted in things that were wrong. And there was a whole case where like the Soviets claimed they found a new kind of water.
Okay.
That led to like the physics community kind of freaking out for a little bit before it turned out to be nothing.
LaCroix.
Yeah. And so, and also just they want to be statistically rigorous because claims about like particles could reshape everything that we understand about the universe. And so a false discovery could have severe scientific repercussions.
Huge.
So you want to be almost near certain. So like one example, one we've seen historical false positives where we found confidence levels that were 3 or 4 sigma that then turned out to actually not be true and cause big issues. So like, I don't know the exact example or how they're saying it, but there was a 750 GeV diphoton excess CP violation in the charm sector. I don't know.
This
something
sounds,
science.
You're making these words up.
Yeah. The other thing too is that oftentimes, like, while that sounds like a really, really small thing, like a really small variable, what will happen in physics is that when you are doing an experiment, you might end up having thousands of different hypotheses. Like you'll we're gonna smash this atom into this atom, and we have thousands of different possibilities of what it could say about science based on what the outcome is. And so they'll then reduce it down to like the most likely outcomes. So when you're dealing with thousands, then confidence variables, you can be really choosy because you want to take if you think of a hypothesis as like a educated guess, and then this experimental result then lets you eliminate thousands of potential answers that fit less good than like the really good ones.
This is something that I think Joe from It's Okay to Be Smart many years ago made a video about, where he said he was trying to explain why we have the term theory, but that theory, it doesn't mean, in the scientific sense, it doesn't mean that we're not sure. That for something to have a theory, or to be labeled a theory in science and physics, all this stuff, it has to go through so much rigorous checking and testing. And it doesn't mean that, I don't know, it's just kind of a theory of gravity. You know what I mean?
It's just a theory, a physics theory.
A physics theory. It's like theory really does mean like, no, this has been rigorously tested. Like it is a stamp of, like it is a massive like seal of importance and approval and justification for something to be labeled a theory. Is like, holy cow, it made it to that level that we're calling it a theory. That is impressive. And I feel like just the average person, myself included, growing up, like you hear theory and you're just like, oh, what? So the scientists just aren't sure? That's silly. But
yeah, a theory is definitely like, it's an explanation that has not had an experiment disprove it yet. A hypothesis is usually like when you usually have a hypothesis when you start an experiment or several, where you're trying to like what you anticipate the outcomes are going to be. And so you might, like, when you start an experiment, do multiple hypotheses about like what the different outcomes could be and what they could mean. And there are some like hypotheses that are like, we haven't been able to do an experiment yet to, turn it into a theory. So we have to call it a hypothesis because we can't do it. But like, then you'll have like, the multi-worlds hypothesis, the sort of idea in physics that there might be other universes or something like that. That's a hypothesis because we haven't been able to do an experiment that could, verify it, but it fits some of the numbers that theoretical physicists, and there's like, multiple hypotheses and all those kinds of things. So that's like, so that's a thing. So then And to keep in mind, like, also that this is also like really hard work, and this is why you have to be really careful too, because we're dealing with like extremely sensitive instruments. We're dealing with like stuff at the very, very edge of like what we even thought was like possible to do. And so we have to be careful with how, how confident we are, like, with our results based on what we come up with, because, we're kind of still playing at the edges here.
Yeah.
So we're still edging when it comes to these things. So
we're still edging these planets.
Yeah. So the other thing too is that because, like, social sciences and medicine and all those things have a lot more variables that you can't control for. In physics, you'll make like huge data sets, and so like getting really high levels of confidence is also more normal, because you can usually actually achieve it, because if you throw a ball against a wall from the same place, the same power,
right,
you should get the exact same result every single time.
Yes,
because
there like the standard in physics is much higher than something like behavioral science, because like there is no equation you can type in to make someone act a certain way all of the, like, 100% of the time, to make every person act the same way 100%. Whereas like, yeah, the throwing a ball example is a great one of like, if you get your circumstances exactly right, like you can have the ball bounce in the same way. Mathematically.
Physics is dependent on that, because physics is all about trying to literally find out like the sort of laws that govern the way the universe functions.
Mm-hmm.
So pretty big deal. And so that happened, and this only got a 3 sigma level of confidence. And also another team that that studied the same thing found signals that are confidence with no significant features actually happening at all, a flat line of results.
Mm.
Jake Taylor over at Oxford did a model agnostic analysis and showed that there are actually no statistically significant spectral features. Luis Wellbanks at Arizona State, a former student of the original team, found that the claims vanish if you use different statistical models to look at the spectra to see what comes out.
Okay.
And a comprehensive data of all JWST data concluded that there's basically just not enough evidence to show that there's any DMS or DMDS. So, like, it very much was like this is not like the team isn't like bad at doing their job. It's just like, this is how science gets done.
You gotta have your peer reviews. Yeah.
Yeah. You propose something, you do like people check and like, critique your statistics models. Like, the things that they're disagreeing with is stuff that like my puny humanities brain would not be able to really speak well to. But like, this is sort of like science is done by teams of people, and so they're like, this is what we found, this is the analysis we did, this is what we came up with, and other people will look at the data, do their own analyses, and they will have their own answers, and there'll be disagreement, and nobody is like, everybody is interested in finding the answer, right?
Yeah. I think that's one of the coolest parts about science to me is when done properly, when you follow the scientific method, at least part of that is going to be peer review. Can you replicate the results? Yeah, exactly. It's like and sometimes an experiment does get results that can't be replicated, and like the cool part about it is you go, well, now we have at least tried it a couple times, and we're even if this didn't work, we're closer to finding an answer, and it's okay to be wrong.
So here is like a little bit of the issues of what they think went wrong. Okay. One is we are dealing with it, like what I kind of said, close to the very edges of what JWST is actually capable of picking up. So when I said they found 10 to 14 parts per million of dimethyl sulphide, that is very close to like the like noise level of JWST. Like that is like from that distance.
Background noise. Okay, yeah.
Yeah, it's so close to being too low to be detectable from like where we're at right now, from that distance and everything like that, to be above like weak signals. And it's all, or at least at that resolution, it's not enough to say that it's DMS and not a different molecule like ethane or something like that similar.
Sure.
Then it also reduced. It took highly sensitive data and then use data reduction techniques to try to find this stuff. So when they got the data from JWST, it's extremely noisy data. There's a lot there. It's huge. And so in order to find these like spectra and stuff like that, they have to do like a bunch of mathematical models to remove a lot of the junk and find like the signal in all that. And a lot of the issues that they seem to come up with is that the model that they used for reducing the data to find the things was based on some assumptions that might have been incorrect.
So that's why when you said, for example, the Arizona State person, Wellbanks, used a different statistical model, the data seemed to vanish from the original findings. So that's what you mean by like one model could have produced one result, different model didn't produce the same result.
Mm-hmm. Yeah, and like they have different techniques for looking at these things because this kind of research is still very cutting edge, and so people have different methods and different things to try and figure things out. But the door's not entirely closed on this because, again, a lot of that is not, it's not that it's not there, it's just that it's far too like at the very edges of what we could possibly detect to be strong. But remember how I said earlier that we can get more confidence by allowing to see more passes. And so they suspect that if we saw to get to like to really like reject, to get to 3 sigma in the same way that they think.
And we gotta get to 3 sigma at least, maybe
gotta
5
get 3
sigma.
Yeah. To get those higher levels of confidence, we're going to have to see a lot more. We're going to have to like have JWST watch a lot more passes of the planet by its star, so that we can get more and more confident that what we're seeing is this molecule that, like, because every time we do that, we'll have more observations. More observations are more data. More data means more confidence, and we can kind of build towards a better idea of what it is. So 25 passes could be a very long time. It depends upon how long the year of K2-18b is.
That. Yeah. Do we know what that is or not yet?
It's probably somewhere, but I did not see it.
Gotcha.
So then there's, then like breaking down then like, well, what is going on here? What could this actually be? And some people thought that it could be other molecules like ethane or other hydrocarbons, which we have even seen in our solar system can be produced without biology. There's I want to say it's Titan, one of the sort of Jovian moons or something like, no, that's a Saturn moon. There is one of the moons of Saturn or Jupiter has a methane water cycle. So it's so cold that water is frozen to like the ice is almost as hard as rock. But methane, it's so cold that methane is liquid, and it has like a sort of like cycle of like rivers and oceans and like rain and like all that kind of stuff of methane.
Wild.
Yeah, space is wild.
That's the methane planet for Star Wars.
Yeah.
You can have that one.
But like that's an example of like, so it could be some of these other molecules that we can actually see don't need biology in order to be produced. The other thing too is they could be right, but there are other forms of chemistry that could mimic these kinds of things. So there could be a different kind of chemistry that we don't know about. And like, after this result came up, a lot of scientists like started like, going to their computer labs and started thinking of like, what are the sort of chemical processes that could happen that are not biological that could result in a molecule like this, and they found that there could be some. The other thing is that, and this is also pointing to like the sort of edges of the things, is that it could be something that's called intrapixel sensitivity variations, which means that, and this is so fucking crazy about how we're dealing with. So when you're doing this kind of research, it's a digital camera, right? Like JWST is a gigantic digital camera. You could have variation, like when you do these kinds of work, you might end up with like an object that is between 2 pixels, and the varying amount of light that we're split by it being between 2 pixels can cause slight variance that can change the data. So this is how small it is on the thing, right? Like we're dealing with an object that is smaller than a pixel, technically.
Gotcha. So it could just be, it just the way that the actual sensor is capturing data could be misrepresenting what it's actually capturing potentially.
Yeah. I tried to get an answer. The closest I got was detection efficiency of light across different regions within a single pixel of an imaging detector.
Oof.
So yeah, we're dealing with extraordinary, and this is also like probably one of the most sensitive digital cameras ever made. So like, I just like kind of want to just put out there like the scale of what we're working with and how difficult this job that they're trying to do actually is.
Oh yeah.
When we're dealing with problems like maybe the difference between 2 pixels could be a problem.
Plus, these days all cameras have some sort of like image processing pipeline and like HDR and whatnot, and like the iPhones are doing like skin smoothing. So who knows what the James Webb Telescope has on their firmware? Like if they updated to the latest,
yeah, they accidentally had the mascara filter on it, and just like
they're like, oh no, it smoothed it out and it gave it such luscious lashes. This planet, oh goodness.
Yeah, and the other part too is that there's a lot of interesting newer research that also implies that DMS might also exist in space without biological results. So recently, a column with a density of very, very low density anyways, was able to find DMS just floating in space. And that meant that like if, say, the DMS was just like in a cloud in space and got between Earth and the planet, it would also show up because the light would have gone through it, right? So,
okay,
yeah,
that makes sense.
And like there are other ways that these kinds of things, like for example, Comet 67p found DMS on a comet. So the Rosetta mission found this and was able to find it. So it has been while the only source of it on Earth that is biological, we have found in space at least some evidence of abiotic, DMS, producing it. And
that's interesting. Yeah, I didn't even think about the fact that they need like a clean line between the photo and the actual like planet and whatnot, because if anything gets in between it, which it will, because there's so much stuff out
space is full of dust and everything too.
Yeah, that it can.
You know, astronomers probably fucking hate dust. Dust is like one of the most annoying, because that shit is all over space, and it keeps getting between us and the things we want to look at. And also it's possible that when we're dealing with chemistry of other planets, but it seems like on planets where there is like, sunlight and a atmosphere that is high in hydrogen, you may actually find that there's chemistry that uses sulfur and would create something like DMS without needing a biological process to do it. It would just happen kind of on the chemistry of specifically like the kind of plants you're looking for, which are these like, hydrogen atmosphere water planets could end up creating these processes. Yeah. And also the other idea is that the concentration that they said being very high, much higher than Earth, does sort of imply that it would probably be unlikely a biological process, because there would not be enough. It would be pretty unlikely that there is so much phytoplankton on this planet that it's producing that much of this molecule. Like it's almost like there's too much of it.
Star Wars says an entire planet of plankton, just the plankton planet. Let's go.
Yeah, like the biological processes on Earth create all sorts of biomarkers that if you were to look at Earth's atmosphere, you would find tons of stuff that are made through biological processes, and they're different. Like if we found a planet that had results of all of those, this is why I think our first detection of intelligent life is going to be finding markers for pollution and industrial processes when we do this with a planet. But you'll find a melange of things, and so you'll find a bunch of biomarkers. Yeah. And so this being, it's kind of almost too clean and too much to suggest biology.
I gotcha.
Yeah. And so we've seen things like this before. One of the more recent ones that I talked about, I think, a little bit at one point on this show, which is that a few years ago, there was the claim that phosphine gas was found on Venus. Phosphine gas is another, it's another compound that we only know of biologically being processed. It produced a scientific backlash, and there was a retraction. Although I heard that there's been a retraction of the retraction, that one's still ongoing.
Okay, cool.
There was I don't know where this is. I don't know where things are at, but basically what happened was like a Korean team made the discovery, and then a bunch of Western teams like said, "Oh, like we didn't detect it when we looked at it." They were like, we looked at Venus and found phosphine gas, and then they were like, the Westerners were like, well, we looked at Venus and we did not find phosphine gas. And what they kind of implied through it was that like, because of like the time zones and stuff like that, when the Koreans were looking at it, it was during daytime on Venus, and they were looking at it at nighttime on Venus, and that might change the chemistry somewhat or something like that. I have no idea. I have no idea where that's going at this point, but that was one of the things that came up.
Yeah. And we've had a lot of other ones like these. I feel like not too long ago, there was that rock that shot in from another galaxy or whatever it was, or solar system or what have you.
That like kind of prompted the podcast was Oumuamua. The sort of,
very true.
And very well, like, you know, like Avi Loeb tried to say that it was a satellite and like all that kind of stuff. It's another really good example though of like, oh, this thing had some weird things. We bought into we dug into extraterrestrial life potentially because it's a thing we really want to be true, but it just wasn't strong enough to make the case. Also, you could say that in 2010, there was this hype around this what's called arsenic DNA, that we found a new form of life, but we found out that it was actually just a contaminated sample.
Oh.
There's also ALH 84001. Yeah, the Martian fossils found in Antarctica.
Let's go.
Were also, you know, most likely turned out to be mineral formations. But we'll see. And things like
or just a real cool potato, a real cool spud.
Yeah. And we've also seen things like the WOW signal, which we were really convinced might have been extraterrestrial communication for a while. But then we've kind of come to the not conclusion, but we've kind of come to suspect that it was probably some kind of terrestrial radio source.
Wow.
Because again, this shit's really hard to do. And yeah, so like the thing is that we have to look at kind of like the Drake equation here, which is that like the Drake equation, the whole like, you know, if you eliminate all the things, you kind of get to life. A lot of the early ways of filling that out made us think that life was going to be a mathematically inevitable thing. You know, the public really assumed that we should have found aliens by now. So there's this whole idea that like alien life is this thing that does it's likely, and it's kind of weird that we haven't found it yet. But the thing is that astrobiology is really goddamn hard to do. And also, like it's super hard to develop because, you know, astrobiologists don't exactly have the easiest time securing funding for their research because that's not it's not a field that necessarily generates a lot of profitable results. You can't really use astrobiology to invent new skin cream or whatever, so it doesn't really make a whole lot of money.
Now, there was the other Drake equation where if you take her age plus 1 and it's 19 or above, she's way too old. So.
Oh my God. Is that why he doesn't talk to Millie Bobby Brown? No, I'm not doing it. And the thing is that this is like not an uncommon thing. Like there was a time back in 1903, there was these proposed N-rays where there was 300 papers published by 100 like, you know, top of the line researchers about a type of energy that doesn't exist. Cold fusion.
Love it.
Cold fusion was...
We love cold fusion around here.
It's the idea of a room temperature nuclear fusion reaction that was unable to be replicated, but was a thing that was, you know, there's a lot of money put into it, a lot of hype about it, and then it turned out to be nothing.
That's the dream.
Yeah. Oh. And then there was polywater, which was what I was talking about, this new form of water in the 60s.
Polywater?
Yeah, it was sort of this idea that they were going to make that there was this polymerized form of water that Soviet scientist Nikolai Fedaykin made in the 60s. it had properties like a higher boiling point, a lower freezing point, and maybe higher viscosity. And they thought that this was like because of the Cold War, they were like, oh, we have like the U.S. needs to make its own polywater. We have a polywater gap between us. And so they thought that there's even like some thoughts that polywater could turn regular water into more polywater and cause like a doomsday effect.
Oh my God.
And so people...
I was going to ask what were we drinking back in the day, but I do know the answer is polywater. So
the answer is lead. This is why we got this.
That's the real water alternative.
That's the real polywater. But by the 70s, people kind of started to doubt that polywater was a thing.
No.
And experiments reveal.
Yeah.
It turned out that what we thought was polywater was probably contamination with things like salt or silica or biological substances, like maybe sweat from one of the scientists or something. And so there's this whole thing. I found this term called pathological science, where you have this experimental error mixed with wishful thinking, leading to a widely accepted but incorrect scientific claim. And I think that that's a really good way. That's a really good like thing to look out for, right?
Yeah, especially on this show. Pathological science.
Exactly. And like there's a lot of pressure to find alien life. Like JWST cost $10 billion. And so there's a lot of pressure to find exciting things with the JWST results. Because to be like, we found another exoplanet where it rains glass sideways is cool. But like that $10 billion secured by a bunch of government grants, what people wanted to find. And even at the end of the day, it's like one of the most revolutionary machines ever built by humans, but it's still limited by, physics and what is like physically possible. We're dealing at the edge of like interpretate, like at the edge of like what we have been able to design cameras to detect. And so we've had to do a lot more processing and interpretation in order to get usable data from it, which leads to all of these interpretation errors that are problems that we're running into, right?
Mm-hmm.
And because it's so expensive, you need to do like, say, justify to Congress or taxpayers that it was worthwhile, because otherwise they might cut. This was less interesting before the bill passed last week, but they had to secure funding for more science, and so they have to find exciting things in order to not do that. But I don't know. I don't even know if NASA's even legal anymore. I have no idea.
All the cool stuff's illegal, like crime.
Yeah. This also deals with one of the major issues in science overall. You might have heard the term publish or perish.
This is sounding suspiciously like we're getting to a part where Tristan makes us sad.
That is true. Should
I play the music?
Yeah, let's make us sad. God damn it. Oh, you got me. You really got me with that one. Shit. Okay. We are in our 30s.
All right, sorry.
I'm in my late 30s.
I was sitting over here fiddling with it, being like, I just want him to get to the part. I really want to get him.
Okay. So on that note, science has
Can I say also that fart sounded like it was pitch perfect for that song. Like
it's true.
It felt like no note out of place.
It harmonized. Yeah. So if you want to be a scientist today and you want to be successful, you have to make discoveries. That sounds like a thing that should be a no-brainer, but it causes a lot of problems. Because that means that if you want to get tenure, if you want to get promoted, if you want to do well, you can't do a bunch of experiments that you then have to report didn't result in anything. You have to make discoveries. You have to make positive results. You don't get awards for not discovering things. And on top of that,
there are no participation trophies in science.
Exactly. Although there should be.
Let's go back to being old men again. Back in my day.
See, I'm a millennial, so when I'm old, I'm going to complain about like everyone has perverse incentives these days because there's no participation trophies.
Yeah.
So the thing is that also, like, another way that a scientist or any academic's sort of career has prestige is through how often they're cited, to the point where, like, people have numbers, like, there's like I don't remember what the number's called, but there's like a number that you can attach to, like, scientists that are based on, like, how cited they are. And so very often, like, bigger claims get more citations, and negative findings tend not to get citations. On top of that, grant agencies tend to reward big breakthrough potential projects rather than small incremental progress. And if you are a new scientist and you're working at a university, one of the things you're going to want to get is tenure. And tenure tends to also, like, you want to get early in your career some sort of big discovery, because then you can kind of pass the tenure process and get, one of those, like, permanent professor jobs that you then can, like, people who have tenure can do stuff like take a year off to focus on research. Usually, like, every, like,
parking too. Sometimes we went to a place that had a specific parking lot for tenured positions. Gosh, gotta get better parking. That's nice.
And the kind of prestige that comes with all of this stuff can play into how you get positions where you can get tenure and all that kind of stuff. And also, yeah, like, you want high profile journals also prefer exciting stories over methodological rigorous stuff. And so if you want to get your stuff in, if you want to get in the Lancet, you have to make a big discovery. You're not going to just get, like, Nature isn't going to publish an article about how you showed that starfish aren't smart.
That's just that old Family Guy joke. Coming up next, can bees think? A new study shows that no, they cannot.
Actually, Kelly, my wife's last roommate before we moved in together, that basically was her research, was can bees think?
Really?
Yeah.
Oh, that's incredible.
Yeah, she was really cool. She did, like, she did, like, a lot of focus on animal stuff. So she did, like, bird stuff, she did bee stuff, and she was a psychologist. She was studying, like, their behaviors and stuff.
Incredible.
Yeah, it was pretty cool. And the other thing too is that universities, they, get new students, they get money, they get all that kind of stuff based on how well their, how the breakthroughs that are happening at their universities do, right? So the results being so hyped might not have been the scientist team's fault, but it could have been the fault of, say, the communications department at Cambridge. Because universities try to hype their research findings to the point where 47% of press releases from universities contain spin that overstate the significance of the results of what they're talking about. Press releases about scientific studies tend to exaggerate or overstate the significance of research findings, using language that frames or makes it seem more important or conclusive than it actually is, to the point where they one study found about 47% of it, which is a lot.
Because it's not even necessarily because sometimes it is about making it feel more important or conclusive, but also sometimes it's about making it sound more interesting too. I remember many years ago I made a video about, like, how Spider-Man sticks to walls. And the only reason I made that video is because there was a paper that came out about, like, what the amount.
How does, like, Spider-Man stick to walls?
No, it was about how a human could, like, using, like, what a human would need, like, the type of, like, follicles or whatever that, like, spiders or geckos and things like that have that allow them to climb walls, and, like, how many a human would need, or whether it would be possible for a human to. And the study didn't mention Spider-Man at all, but every single publication, like news source, every online publication, everything framed it around, like, here, Spider-Man. Could Spider-Man exist? Here's how you could be Spider-Man. And it did, like, the actual study doesn't mention Spider-Man at all. in any capacity, but everyone was like, Spider-Man, Spider-Man, Spider-Man. And that's the only reason I made a video about it, is because everyone was being like, it's the Spider-Man research paper. And it's like, it's actually not, but everyone is publishing it like it is, because they just need it to sound interesting.
Yeah, Dr. Parker of Queen's University seems to be very disinterested in talking about Spider-Man in his paper.
Yes. Yeah. And honestly, I've got some doubts about this. There was this guy, Jameson, who was saying that Parker's research was shoddy at best.
J. Jonah Jameson is totally a Trump supporter, right? I think we can all just agree on that one.
I think so, but I think the comics would make you believe, because we can't get into it, but like comics are very much just like the people who run comics a lot of the time, like the writers and the publishers, are very much like, but no one's actual. You still need to like a character, and like even the most evil person you can think of isn't that bad in the world of comic books. And it's like, okay, come on, guys. You can write a character who's a Republican. It's fine. No one's going to get upset.
J. Jonah Jameson is definitely a Trump supporter. We said it here first. Yeah, so the thing is that oftentimes like a researcher will do will write a paper, and when you write an academic paper, you write something called an abstract at the top, which is sort of like a 1-paragraph distilled version of what you did and what you found. And oftentimes it's trying to put its best foot forward to say its significance, because oftentimes if you're like, sifting through a bunch of articles, you'll read the abstract to kind of just get a quick thing about what it's about, and you want it to be kind of scientific clickbaity almost. Not clickbait, but you want it to be like it's like the title or thumbnail of a video, right? You want to have like the best, catchiest thing.
Yeah.
And then the people who, like a lot of communications people, like they'll start with just that, and then they'll go another length to like try to make it more interesting and sexy. So it's like bait on top of bait on top of bait.
Yeah, I mean it's literally like all the scientific communication publications were all doing the whole like this research paper shows what it could be like to be Spider-Man, and the paper itself has nothing to say about actual Spider-Man, but everyone was like, how can we make this clickable? How can we make it so people click on our website?
Exactly. And there's there's a lot of other like perverse incentives at place. Like, for example, there's like social media platforms tend to promote exciting things because of novelty, but potentially push false information, while like correction asymmetry, like it takes a lot more work and it gets a lot less attention to debunk something than the original claim. One case would be a podcast called "It's Probably Not Aliens," where it critique a show that has millions of viewers and has made every single person associated with it stupidly wealthy.
Yeah, and how are we doing? Support us on Patreon.
There's also like other things, like space agencies need public support from the government to do expensive missions, like put the most sophisticated digital camera ever made into space to look at exoplanets.
Send 4 attractive people to travel through cosmic radiation and come back as superheroes.
Mm-hmm. And when you saw like the polywater gap, right? Like also there's a space race angle where like countries in competition with each other. Like right now, there's going to be a pressure to find stuff because America is very close to, in space, having China's space program basically completely devour its lunch. They're about to lose the race for the moon and moon bases, and like China's like really progressing. And so there's definitely like a national competition angle where like they want Western they want like they want to do like Absolutely. It's part of like national power and power struggles.
I made a joke about the Fantastic Four just then, but quite literally the original draft for the Fantastic Four was having them go to Mars, but Stan Lee wrote in the margins of his original script that he was worried that the Soviets would actually genuinely have landed on Mars by the time that the comic came out, that he changed it to they're just going to travel the stars instead because it made it more vague. So it's exactly, there's history of that space race angle too, of just trying to one up other countries and whatnot.
Yeah, and we're in it again, so there could be a lot more thing. The other thing too is that in like, democratic countries, that public funding then negate or needs like has an obligation for exciting discoveries, because that gets votes, that gets like support for public funding of science is, I mean, this year alone, but like nonetheless, even before things went really crazy, like to justify science to voters in America, you have to like be, we discovered a way that makes the hair on your penis grow back, or whatever it is that people want. It makes your scalp hard. I don't know.
Doctors hate.
Yeah.
hair.
So like, you need to have exciting things happen now. And this is the new section that we're trying to do. I want to have some stuff about what you can do.
Oh, okay. I don't have a stinger for this.
I have one
hold
idea.
on.
Yeah.
This is maybe something we can build off of.
How do you move it?
How do you move the needle on this, Tristan?
I thought you were going to push the fart button again.
No, I think that'll do.
How do you move it?
We'll just get a clean take of that one more time, and oh, sorry, that was the wrong one.
Your finger slipped.
My finger, it's literally right under it. That's my bad.
So one of the things that would be good for everyone to have an idea about, especially when it comes to looking at scientific discoveries and the way that science works, is understanding the statistics behind it. P-values, for example, which is sort of the probability that the result is, like statistical noise or whatnot, is important. Like confidence intervals, statistical significance, the whole 3 versus 5 sigma showed
know your sigmas.
Know your sigma. But like that shows like how that was a perfect example of how the more extraordinary the claim, the more you have to be very, very confident that what you're saying is true. And realize that like, yeah, there will be a lot more certainty in like, the news article, but when you get to like the scientific article, you're going to see a lot more uncertainty, a lot more might, could have, preliminary hints, things like that. And like sometimes a study will come out that didn't have a huge sample size, wasn't like a great experiment, but the idea wasn't to like, this definitively shows this. It's like, hey, this might be something to look at. And sometimes that will, like, this is just very preliminary, just a thing we just thought might work. And look, we got something interesting. Maybe we should do more research. And that'll get turned into, we discovered this. And all of a sudden, people think that it says a lot more than it does.
Yeah.
And so, and the other thing, too, is that you should probably also be wary of what are, like single studies. Really, like, when we understand how something is going to, like when we make real discoveries, there's going to be, confirmation, in like replication, independent analysis, and the move towards it will happen over time. That's so
yeah.
Don't, and it's like, yeah, you like, look out for things like press releases and news articles. If you can, I mean, this is unfortunately fairly paywalled, but, keep your eye on like the actual sources and look for like, big words trying to do like superlatives, like revolutionary, paradigm shifting, because very few scientists publish papers where they say things like this is a paradigm shift, a revolutionary thing, because scientists is.
If it sounds like a prestigious sort of twist on a Mr. Beast title or thumbnail, it's probably, maybe do a little more research into it. Maybe look into it a bit more.
Yeah, exactly. The other thing is that conflicts of interest.
I spent 20 days locked on the fart planet. It was revolutionary. And then I won $5 million or whatever. I feel all of his involve money somehow. I don't get it.
I have never seen a Mr. Beast video, nor do I really want to, so I have no idea for now.
No.
But yeah, like things like there's a lot of times conflicts of interest. Like one of the really good examples that I kind of came across recently was the Wakefield study, which was the sort of study back in the 90s that tried to make the claim that vaccines cause autism. And
I was going to say, is that Andrew Wakefield?
And the reason why the reason why Wakefield did it wasn't just because he was a shitty scientist. It was because he was paid by a lawyer who was trying to do a class action lawsuit against a vaccine manufacturer. And you very often will find conflicts of interest like that. Like maybe that study that shows that cigarettes are actually good for you turns out, that might have been published by Philip Morris. Interesting. Okay. or a team that got money from
it. Also famously, I believe Andrew Wakefield was offered several times by other, organizations to fund him, like they would fund him replicating his own study, and he kept turning it down and continues to turn it down. Almost like he knows that it's wrong.
Yeah. Here we go. The other thing, too, is that, the peer review process is in need of some changes. There's a lot of, new attempts to try to, find a new way to do peer review. Peer review has holes in it. And just saying that you had a few other experts read the work and also agree with it is, it's not necessarily ironclad. And there are some thoughts about what we should go for. One example that I think is really interesting, that was one that was kind of being played around with, was that you might be able to get pre-experimental publication approval. Like a journal will, you'll say you're doing this experiment, and a journal will say, we will publish the article you write about it, no matter what your result is. And so that it's going to get in the journal no matter what happens, and you are locked into giving the result no matter what it is. And there's also some talk about doing more post-publication review, more systematic replication and things like that. And just one of the things that you listener could do right now is realize that scientific consensus is something that takes years to build, not revolutionary discoveries that change everything overnight basically don't happen. Scientific changes in scientific understanding take years, decades. There's even a whole thing where there's this paradigm shift thing that showed that a lot of the really big ideas and in some scientific fields don't actually get to change until the sort of intellectual leaders of the previous paradigm die or retire.
I was thinking that, but I didn't want to say it because it sounded rude or grim. But yeah.
Mm-hmm. Yeah. And the other thing too is that uncertainty is a normal thing. We don't like uncertainty, but unfortunately we live in a world that is very uncertain, and we have to kind of know that is the first time that we discover extraterrestrial life, we're probably not going to be confident of it for many, many years, because we're going to be doing everything we can to try and see if there's another explanation. And that's a good thing.
Yeah.
And that things getting shut down, people might think that this is kind of a bummer, but this is how science happens. Fixing mistakes and not avoiding them is how science advances. So this is actually a good thing, because in doing so, we're learning stuff about the statistical processing of JWST data, about spectroscopy. All those things are being advanced by this research. Mary Poppins, yeah, exactly. And so also, if you want to follow science, maybe you should follow trained science reporters. So I looked it up. The BBC has pretty good science correspondents. One example was Palab Ghosh. There's one publication called The Conversation that hires academics and researchers to write articles that are then edited by professional journalists for clarity and accuracy.
Okay.
There's also publications through ScienceX. They run websites like Tech Explore, Medical Express, or Phys.org that do pretty good science reporting, and also National Geographic.
Yeah.
Places that basically have... Yeah. Places that have places that basically aren't in the American media ecosystem, and also have a lot to lose for getting things wrong.
Fair enough.
And yeah, just, we humans really love confirmation bias, and we always have to be aware and fight it at all times, so that I think I've said this on the show multiple times, but if you hear a claim that aligns with the way that you understand the world, that's when you need to be the most skeptical, not the least, because bad data plus a desire to have the outcome of that is what leads to a lot of what leads to a lot of the shit that we cover on this show.
Absolutely. I mean, you and I make educational, informative kind of videos outside of this podcast and whatnot. And I don't know about you, but I feel like one of the things that I do once at the start of my research and once again at the end of my research is I try to find things that would disagree with the sort of conclusion that I came to, just to ask I'll ask like people to look over a script if I have enough time for that. Other times I'll just try and like search inward and be like, what would someone disagree with about this conclusion? Like what is bad about this? Like what could someone argue against, to sort of, number one, cover my bases and sort of preempt comments, but also number two, to make sure that I'm not like really stretching something thin. And I do catch myself a lot of times being like, I came into this topic with an analysis that I wanted to reach, rather than doing an analysis and seeing where it actually takes me. And that can be hard, and it also can be like, especially in, we're talking about like people publishing things, it can be time consuming, and you can lose a lot of time if you realize far into the process that like the conclusion that you want to be true is not the one that is. You're having to make a lot of reaches, a lot of stretches, and it's like not working. And so it can be much more beneficial, monetarily, to just sort of brush it off and be like, it's faster and easier to just publish this thing that I already agree with and whatnot. So it's challenging, but it's rewarding to like question a thing that aligns with your beliefs, because sometimes it is true, but sometimes it isn't, and then you learn a little bit more.
Yeah, turns out one of the hardest things to deal with in our world is that doing things right is a lot harder than doing things fast.
Yeah.
The other thing too that we can look for is that NASA has actually put together like their framework for evaluating claims of life, and it's a pretty good one to look for, which is like one. It's called the COLD scale. So one, which is the confidence of life detection scale.
Ooh.
So number one, detection of possible life. Then you have to rule out whether it's contamination, like something like what we find with like
dust,
the sweat and
like biological samples from sweat, things like that.
Then make sure that the biology in the thing you're looking at is even possible. So do the modeling, try to find out if this biology could happen. Then rule out non-biological processes, like the idea of like, hey, look, we found like there are abiotic ways to produce this kind of chemical or something like that. Then
farts can exist in and of themselves.
Mm-hmm. The other thing is you want to find a independent signal. So like if we got signals from ET, we wouldn't want to just see one broadcast. We want to see multiple broadcasts to kind of confirm it, and then try to rule out other hypotheses, and then do an independent confirmation, and then we can like say like nothing has ever gotten this far yet, obviously, but and the other thing too is that single molecule detections should be more skeptical, because we'll probably see on a planet with life where there's a lot of biological chemistry going on, many biosignatures that are not just like one gas. Yeah,
lots of things.
Yeah.
One
cannot have biology on farts alone.
I've always said that, Tristan.
And so, and also just know that right now, this kind of research is being done at the very limits of what our instruments can actually do. And maybe life won't be detected with JWST because we haven't been able to build a, thing. Maybe that whatever we replace JWST with will be the thing. Who knows? Maybe the Xi Jinping space telescope that gets built in like 2045 will be the one that discovers it. Or maybe we won't know if there's life on the moon until the Chang'e 3 mission in 2030 lands on the moon.
Until the new iPhone comes out with that new camera processing power that can really make things shine and shimmer in all the right ways.
But one thing you can do to move towards the possible detection, because you'll find out about it 3 months after it happens, on the podcast It's Probably Not Aliens, which you can follow along with the probs not... Oh, you have a thing? Do a sting? Okay.
No. You were just saying to move towards it, so I was going to say... I was going to do that again because
yes,
that felt pretty good.
So
I always forget I have
So
that
you
one.
want to, the thing you want to do is you want to go to probsnotaliens.bsky. So Probs Not Aliens on Blue Sky. That's how you do it.
Just find Probs Not Aliens on Blue Sky and all these other places you can find us. Tristan and I, as I mentioned, have our own YouTube channels outside of this podcast. I really need to make some videos this year. I am, yeah, that's me right now. I'm struggling. But Tristan, where can people find you?
I have a YouTube channel called Step Back where I occasionally now make videos about history and the world and why it's important to look at things in larger contexts. And I'm working on a video on Hindu nationalism that maybe will be out by the time this episode drops. I have no idea. I have an interview next week that's kind of the end of my research phase. But it should be a good time. I wanted to know, though, Scott, why do you think Coolsville sucks?
Oh, that is an that's an April Fool's Day video that I made that's only up on Patreon and for members on YouTube. I missed April Fool's Day by like 2 or 3 days this year, and so I have it scheduled for next April Fool's Day. So you can watch it a full year early on Nebula.
Oh no, did I spoil it?
No, it's fine. People know what it is. It's just they can't watch it unless they watch it on Nebula or on YouTube as a member of my channel. But yeah, my YouTube channel is called NerdSync, NERDSYNC. I make videos about comics and cartoons and Scooby-Doo. I'm trying to do a lot of comic book stuff this year again. I dipped my toe into Scooby-Doo a lot, and I'm still going to. But there's a lot of comic book movies that are making me excited about comic books again. From Superman to Fantastic Four, even Thunderbolts I thought was pretty decent. But in the run-up to Superman, as of this recording, it's not out yet, I am making a video about the history of the real origins, the real-life history about the creation of Crypto the Superdog. And what's really interesting about it for me is that there is no one origin. There are 3 potential competing origins with some overlap. It's very exciting to sort of pitch ideas for how the character was created. I don't know. It's really interesting. I hope I pull it off okay. But if that video isn't out by the time you're listening to this episode, bully me. Please bully me into posting videos.
If Scott's crypto video is dipping, you need to buy that dip and harass him into making
Buy it low, sell it high. Actually, don't sell it. Ride it to the moon, like crypto would want.
Moon adjacent.
Does Krypton have moons? I don't even know if the planet Krypton has moons. It probably it does because I don't know. It doesn't matter. All right. You can also find this show on Nebula, nebula.tv/probablynotaliens, where you can get episodes early, I think.
Yeah.
Is a thing that we're still doing. Either way, it just supports us by listening to us over there, as well as supporting this show over at patreon.com/probsnotaliens. It really helps us out when you support us there. You get, again, episodes early. It's just a little bit more money for us to do things like pay editors and, upkeep equipment and things like that. And, it just means a lot. So we appreciate everyone who does that. And tell your friends about the show. Write reviews on all of the podcast platforms. That helps us out as well. As you can see, we've got a plethora of ways where you can help support the show, from direct support monetarily to writing reviews. Really helps. Telling your friends also really helps. So all that stuff is great, and a great place to send people to learn about this show is a little website called probsnotaliens.com. It's got links to all the things that we talked about here for how you can support us and find us and all that great stuff. Tristan, it has been a pleasure talking to you for almost 2 hours about farts. This has been wonderful, and I can't wait to do another episode with you very soon. But until then, my name is Scott Nicewander.
I'm Tristan Johnson, and the truth is out there. 3 Sigma. I was waiting for it. The truth is out there.
Fart.